So let's start this lecture. I will keep talking about one-dimensional flows. So this is given by equation x dot equals to some function of x. So it's consider autonomous equations. Now, I never put it before, but we should use certain conditions for flow generating function f. So for example, well, it should have at least first derivative, and this first derivative should be continuous. We put it like this, C1. C1 means f function f of x has derivative for any value of x, and this derivative is continuous. So here another point is about domain for x. We can assume that x belongs to, so it could be any real number, for example. And again, we are not interested in finding exact solution in integrating this differential equation. It could be, well, it could be even impossible, or could be very difficult. So we want to use so-called quantitative analysis to have a grasp of what kind of dynamics we can observe in the system described by this differential equation. So it has a family of solutions. So this is x of t. And so this, to get a unique solution, we need to apply initial conditions. Initial conditions. Xz times 0 equals to x naught makes the solution unique. So it's again, so we are not looking for exact solutions. We use qualitative analysis, and there is one important reason or one advantage. One advantage which comes with this kind of differential equations, namely solutions. Let's say x1 of t and x2 of t do not intersect. So this is important property. This comes, I was talking about this last Wednesday. So this comes from, this is time, this is x. So this function f of x defines so-called direction field. If we take some value of x, then f of x equals to some constant here, because it depends only on x, and f of x is a slope of solution. And therefore, this line is crossed by all solutions. For example, this is solution, this is solution, this is solution, and so on. They all cross this line under the same angle. And it means that no intersections can be observed. Because intersecting solutions would mean that we have two different slopes at the same point for the same value of x, which is impossible. And this is the main point. To analyze dynamics in the system, what we do, we find fixed points. which are roots of this equation of x equal to 0, which means x dot is 0. So when we find fixed points, let's show it. So assume this is our function x, f of x. Then we have fixed points here, x1, this is x2, this is x3, so 3 fixed points. Now next point is, so each x equal to x capital I is a solution, by the way. And it can't be crossed by any other solution. And therefore, x capital I's fixed points set boundaries to domains in domain in, so subdomains, let's say, subdomains in the domain for x. So this is, for example, this subdomain is D. Let's say this subdomain is D1. This is D2. This is D3. And this is D4. So we have, for example, in this particular case, 4 subdomains. Now, next point is if our initial condition in certain domain, let's say in domain D1, then it can't cross fixed point x1, and therefore our solution will be always in the domain D1. If x0 belongs to Di, then x of t also belongs to Di for any time. So it doesn't leave these domains. It is first observation. And finally, last observation is what is going on inside of domains. For example, here function is positive. Positive function means x dot is positive. X dot is positive means that x is increasing over time. So here we have increase over time. Here the function is negative, and therefore x is decreasing over time. Here it's increasing over time, and here it's decreasing over time. And now we can say even more. We can say that if x0 belongs to D1 or D2, then x of t tends to x capital 1. So x1 is stable fixed point. Stable fixed point. And this D1 and D2, all this area, is domain of attraction. For x1. And this would be the domain of attraction for x3, at least for this illustrative function f of x. And so D1 and D2 is domain of attraction for fixed point x1. This can be summarized like this. So we have x-axis. So we have values of x1, x2, x3. So if x0 was lesser than x1, we will have increase, so our functions fxt are increasing functions of time, and they reach in the limit to infinity, they reach x1. And here between x1 and x2, there is these are decreasing functions, our integral curves, also reaching x1. Here it's increasing, it's decreasing. So all of this is called, so at least what we know here. So we can, if someone gives us x naught, the initial value of x, we can say straight away in what range our solution is appears to be, and to what is its limit when time tends to infinity. So all this x-axis with all these arrows, directions of orbits, is called, generally it's called phase portrait, but in one-dimensional case, it's called phase line. Good. So this is a summary of what we have spoken about last week. So today we extend this story. So for now we considered this flow x dot equals to f of x. And now we go to more complicated story, x equals to f of x and c. C is parameter. And now, so here we had x1, x2, say x3 fixed. This equilibria are fixed, but now we will have x1, say x1. It depends on parameter c. x2 also depends on parameter c. So location of equilibria now changing depending on c, and their stability also, stability of xi also depends on c. So this is important part. We had it before for maps, and now we will consider this phenomenon, namely bifurcations for flows. Let's consider example. So example is very simple. X dot equals to x squared minus a. So fixed points. Roots of this algebraic equation x squared minus a equal to 0. And we have two fixed points, each equal to plus minus square root of a. And they exist if parameter a is positive or negative, let's say. And for stability, we have this function f of x, which is x squared minus a. We find its derivative, which is 2x, and then find the derivative of f when x equals to, say, square root of a, and this will be equal to 2 times square root of a, positive. Therefore, x1, which equals to square root of a, is unstable. And derivative of f when x equals to minus square root of a equals to minus 2 square root of a negative. Therefore, x2, which equals to minus square root of a, is stable. And bifurcation diagram looks like this. So this is x, this is a. So we have two fixed points, they exist when A is positive, plus square root of A is unstable, and minus square root of A is stable. So this is bifurcation diagram. So we now already know that this kind of bifurcation is called fault bifurcation. Now definitions. So definitions. First definition. So two equations let's say x dot equals to f of x and y dot equals to g of x are called topological equivalent if there is transformation say x equals to h of y or the way around, where h of y say has continuous derivative such that all orbits of first equation transfer into orbits of y dot equal, sorry, here g of so this means that we can deform, so we can deform space xt such that it transfers into space yt, plane yt. And in this plane, all solutions of all orbits of in terms of x transfer into orbits in terms of y. So this is for two different flows x equal of x dot if f of x and y dot if g of y, but this can be, this topological equivalence also can be extended to flows with parameters. Let's put it like this. So second definition. Flow with parameter is called structurally stable if x dot equal to f of x c is topological equivalent to x dot equal to f of xi star, different value of parameter c, if for all c star in vicinity of c. And next definition, definition 3, value c equal to c star is called bifurcation value if x dot equal to f of x c star is not topologically stable, is not structurally stable. So this means that we in the vicinity of C star, there are values of C such that is a number of fixed points or their stability pattern is different. This second definition about structural stability can be stated about in terms of delta neighborhood. Let's put it like this. Structural stability. X dot equal to f of, let's say now, C star. That's C star is fixed value of C, is structurally stable. If there is delta such that for any C in the vicinity of C star, f of xc is topologically equivalent to f of xc star. Okay, and to make easier all other statements and analysis of different bifurcations, we will make the following transformation. We will make the following statement. We will assume that x dot equal to f of xc has an equilibrium at xc equal to 0, 0. So this is easy always to transfer this system to get if x dot equal to f of xc has an equilibrium at xc equal to, for example, x star, c star, then we can make a transformation. We can make substitution. Say y equals to x minus x star, a equals to c minus c star, and in terms of then we will have the flow y dot equal to f capital dot y a, and here we have an equilibrium at ya equal to 0, 0. Well, it's pretty much obvious. You don't need to prove it. Now our first theorem. Assume x dot equal to f of xc has an equilibrium at 0, 0, and derivative of f over x at 0, 0 is non-zero. Then for small values of c, let's put it like this, for c around 0, we will have an equilibrium x around 0 with the same stability of the same stability. So what it means? It means that if C is slightly changed, our equilibrium will also slightly change, but its stability is not going to change. So this is easy to prove using first order approximation of function of f of xc. So x dot, which is f of xc, first order approximation around 0 will be f at 0, 0 plus derivative of f over x at 0, 0 times x plus derivative of f with respect to c at 0, 0 times c. So this is approximation, first order approximation. So this is 0 because it's equilibrium, and therefore x dot will be equal to derivative of f over x times x plus derivative of f over c times c. And equilibrium for this is found from this condition. So this should be equal to 0. Or we get x equal to minus derivative of f at 0 with respect to c divided by derivative over x at 0, 0 times c. So if c is small, x is also small. And next point is about stability. Stability is given by sine of f of x. Derivative of f with respect to x at 0, 0. So defines stability of 0, 0. But this sign, so if f of x c belongs to c1, then derivative of f over x at x c continues. And this means that there is area around 0, 0, where sine of f prime of x is the same, where sine of derivative of over x c is not changing, which means that x equal to minus derivative of f over c divided by derivative of f over x 0, 0, 0, 0 will have name stability as 0, 0. This equilibrium where, let's say, x star, c star, where derivative of f over x at x star, c star is non-zero. It's very important. That has special name. Is called hyperbolic equilibrium. And what the theorem which was shown earlier, it's generally what it states is this. Hyperbolic equilibrium so hyperbolic, let's put it like this. X dot equal to f of x c, which with hyperbolic equilibrium only is structurally stable. So what it means? It means if, again, we have this map, it may have quite a few equilibria, but if all of them hyperbolic, then small changes of parameter c will result to small shifts of equilibrium, but it will not change their stability, and therefore this flow will be structurally stable for these values, for this value of c. Okay, so this was a preliminary definitions and theorems, and I will go through classification of bifurcations starting from the next lecture.